Welcome to The Explainer. Today, we're going to unlock some of the absolute coolest mathematical secrets behind how we actually trust our data. If you've ever stared at a data set and thought, is this the whole truth, or did I just get a really weird sample? Well, you're in exactly the right place. We're diving into the incredibly rigorous and, honestly, beautiful world of concentration inequalities. Let's jump right in.
So ask yourself this for a second. How much can you actually trust your finite sample? This is literally the fundamental problem of data science. In the real world, we never have access to all the data in the universe, right? We have to rely on empirical averages from a strictly limited data set to represent the true underlying reality. If you flip a coin 100 times and get 60 heads, how confident are you that the coin is actually biased? How much weight does that finite sample actually hold?
Which brings us to our first main section, empirical averages versus true expectations.
Now notice the stark contrast here. If you've taken stats, you definitely know the law of large numbers and the central limit theorem. Those are asymptotic limits. They basically tell us that as our sample size, n, approaches infinity, our empirical average converges perfectly to the true expectation. But here's the catch, and it's a big one. Infinity is a luxury we literally never have in practical machine learning. Our data sets are always finite. It could be 1,000 data points, it could be 1,000,000, but it's fixed. And that is exactly why we desperately need the right side of this equation, non-asymptotic bounds. We need ironclad mathematical guarantees for a fixed, finite sample size.
So, how do we solve this non-asymptotic problem? Enter our main topic. What exactly are concentration inequalities?
Well, the secret is right here in the definition. A concentration inequality provides a probabilistic bound that measures how far a random variable, like our sample average, deviates from its true mean, specifically for a fixed sample size. Think of it as a statistical safety net. It doesn't just wave its hands and say your sample average is probably close to the truth. It gives you the absolute worst-case mathematical scenario for exactly how far off your data's average could possibly be. It bounds the tails of the distribution, proving that huge errors have exceptionally tiny probabilities.
And the source text hits the nail on the head here. This quote brilliantly illustrates the whole paradigm shift. Unlike the classical limit theorems, it is non-asymptotic in that it holds for all fixed n. This is precisely why these bounds are the absolute bedrock of modern learning theory. You don't have to wait around for infinite data to make a rigorously backed claim.
All right, let's look at our first specific tool. Section 2, Hufting, the reliable workhorse.
Hufting's inequality is almost always the first tool you're going to pull out of your probabilistic tool belt, mostly because it's incredibly robust. The key assumption here is just beautifully simple. Your independent random variables only need to be strictly bounded within a specific interval, a to b. That's the whole shebang. Notice what we don't have here. We don't need to know the variance of the data. As long as you know the absolute max and min values your data can take, Hufting goes right to work.
Let's look at how you actually apply this in 3 steps. First, just verify your variables are independent and bounded. Simple enough. Second, you calculate your empirical average or sum. And third, you plug those directly into Hufting's formula. What you get out the other side is a rock-solid guarantee of exponentially light tails, meaning the probability of your sample average deviating from the true mean drops off exponentially as your sample size grows. It plummets so fast that you can be highly confident in your sample incredibly quickly.
Now, Hufting is fantastic, for sure, but it can sometimes be a bit, well, conservative. It's essentially planning for the worst-case scenario, using only the bounds of your data. So what if our data involves something like highly skewed coin flips with a super small probability of occurring? Or actually, what if we do know the variance? Can we tighten up that safety net?
That brings us to Section 3, Finer Bounds, using Chernoff and Bernstein inequalities. These are our precision instruments.
First up is the Chernoff bound. Chernoff is highly sensitive to small probabilities, especially in Bernoulli trials. You know, your classic yes-no coin flips. If you have a wildly biased coin where heads only comes up maybe 1 in 1,000 times, Hufting's inequality gives you a bound that's just way too loose because it only cares that the coin is bounded between 0 and 1. Chernoff, though, it factors in that tiny mean, perfectly capturing what mathematicians call the true Poisson tail. It essentially adapts to the extreme skew of your data.
And then we have Bernstein's inequality. What's really cool here is how Bernstein acts as a direct, powerful upgrade over Hufting. Bernstein incorporates the absolute bound of the data plus the variance. So if your data happens to have a very small variance,
meaning it isn't fluctuating wildly, Bernstein rewards you. It gives you a much tighter, sharper limit on your error. It actually operates a lot like a non-asymptotic version of the central limit theorem. Looking at the big three side by side like this makes it super clear when to pull each specific tool from your belt. Only know your debt is bounded? Use Heffingding for a reliable general bound. Dealing with independent binary trials with tiny probabilities? Grab Chernoff. And if you have bounded variables but you also have a solid handle on the variance, you absolutely use Bernstein to get that perfectly tight, optimized bound. It's all about using the right mathematical tool for your specific data environment.
Okay, let's bring all this abstract math back down to earth for Section 4, Applications in Machine Learning. Why does a machine learning engineer actually care about all this?
Well, to answer that, we have to look at the central dilemma of machine learning. When you train an algorithm, you only ever get to measure the empirical risk. That's just the error your model makes on the specific training data set sitting on your hard drive. But that's not what you actually care about, is it? Your ultimate goal is to guarantee a low true risk, the expected error your model is going to make tomorrow, out in the wild, on unseen data. So how on earth do we bridge the gap between empirical risk and true risk? We bridge that gap using concentration inequalities. Seriously, they are the mathematical bedrock of learning theory. They allow us to bound empirical risk minimization, giving us a mathematical guarantee that a model minimizing training error will actually perform well in production. They help us establish strict generalization bounds. They even let us calculate advanced stuff like Rademacher complexity, which measures how well a model class can fit random noise, and they do that by directly relying on Heffing's inequality to bound the expectation of the maximum error across all possible models. Without these inequalities, machine learning is literally just trial and error. With them, it becomes a rigorous science.
Which brings us full circle right back to this foundational quote. The primary goal, then, is to relate empirical averages to expectations. Everything we do in data-driven science hinges entirely on this one connection. Concentration inequalities are the bridge that safely carries us from the limited, finite data we observe over to the infinite reality we're actually trying to understand.
So I'm going to leave you with this final thought to ponder. The next time you see a machine learning model bragging about its 99% accuracy on a training data set, ask yourself, is that model truly learning the underlying reality, or did it just get incredibly lucky on that specific sample? Thankfully, because of Heffing, Chernoff, and Bernstein, we actually have the math to find out for sure. Thanks so much for joining me for this explanation, and keep questioning your data.